Okay, so today we'll talk about some I'm sorry, can we put away all the cell phones back here? Can you put away the cell phone? Away, meaning away? Yeah? Okay. Okay, so all right, so today we'll talk about some important distributions. Now you'll notice something common to all the distributions that we'll talk about, that somehow they have to do with coin flips. Okay, so every distribution we'll talk about today has to do with coin flips. And it's not a coincidence. Okay, so somehow what will end up happening is that we are going to be, these distributions are very interesting. They're important because they model something in the real world. It'll allow us to understand some kind of real world phenomena. And it turns out that many of these real world phenomena you can think of as somebody behind the scenes flipping coins, just lots of coins. And then you're observing some random variable relative to that. So let's try to see what these distributions look like. So we'll start with the easiest one. Okay, so if you don't mind, I'm going to belabor the point, and I'm going to make sure we understand the basics, and then we'll go ahead and we'll look at more and more complex distributions. And as we do so, it'll be useful that I'll belabor the obvious and do the, make sure you remember your, the basics about random variables and so on. Okay, so the first probability distribution we'll look at is the binomial distribution. Okay, what's the binomial distribution? Okay, so there's an experiment underlying it, which is we have a bias coin with probability of heads equal to p, and we flip this coin n times. And what we are interested in is a random variable, which we may as well give the correct name of it today, which is S sub n, which is the number of heads in n flips. Okay. And what we are interested in is the probability distribution. So what does it mean, the probability the distribution of this random variable? What it means is we want to know what's the probability S sub n equal to k for every k. Right? And one way we can depict this is by plotting the distribution function. So here's k, and here's the probability S sub n equal to k. That's what we are plotting up on this vertical axis. And then we get some sort of a distribution function which looks like that. Well, actually, it doesn't look like that. It actually looks like, it looks like that, right? Because it's integer, right? So at every integer point, it sort of goes up a little bit or goes down a little bit. But of course, what I'm doing is I'm approximating it by this curve. Right? Is everyone clear about this? So what I mean is, okay, so let's say if this was 0, 1, 2, 3, 4, 5, etc., then it doesn't really look like a curve like this. It just looks like what's the value at 0, 1, 2, 3, 4, 5, and so on. That's what the probability distribution is. It's the value. What's the probability S of n equal to k for k equal to 0, 1, 2, etc., etc. So this is the probability distribution function, these crosses. But then what I'm saying is, well, let's just blur our eyes and look at it as a continuous curve. Right? That's the rough shape of it, but the distribution function is really these crosses. Right? So, okay. And then you know that this number is actually n choose k, p to the k, 1 minus p to the n minus k. Right? The probability you get exactly k heads is the number of ways of getting exactly k heads out of n is n choose k. And then for each such sequence, if you know the locations of the k heads, The chance of that is, well, the chance you get heads in all those k locations is p to the k. The chance you get tails in the remaining n minus k locations is 1 minus p to the n minus k. And so that's the probability S sub n equal to k. Now we also talked about what's the expected value of x and what's the variance of x. And in order to write down the expected value and the variance, what we did was we wrote x as x1 plus x2 plus dot 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 plus x sub n, sum of n random variables. X sub I is 1 if the ith flip is heads, and 0 if tails. And now we could say the expected value of each x sub I is equal to p, and therefore the expected value of x, by linearity of expectations, is the expected value of x1 plus expected value of x2 and so on, is n times p. And similarly, because x1, x2, and xn, all these are independent random variables, the variance is n times the variance of x sub I. But what's the variance of x sub I? It's the expected value of x sub I squared minus expected value of x sub I whole thing squared. But x sub I squared is a random variable which is also 1 if when you square 1 or 0, you get back itself. So x sub I squared is the same as x sub I. So this is the expected value of x sub I minus expected value of x sub I whole thing squared. And that's p minus p squared. Right? So you get n times p minus p squared. That's p times 1 minus p. And that's the variance. Okay? So that's a binomial distribution. It's a probability distribution which looks at this random variable, which is the number of heads you get in n flips of a biased coin. And then the distribution function itself tells us what's the probability S sub n equal to k for every k. That's a lot of information. And so instead we look at the expectation and variance, and that already gives us a lot of information about the random variable. Okay, so this is one random variable. It's a particularly important one. It comes up all over the place, right? Because you can imagine that there are many, many situations where you have a number of choices that take place, and you want to know how many of them were successful. Right? You're transmitting messages over a noisy channel. You want to know how many errors were there. Well, if each time you transmit a bit or a character, there's a probability p of an error, how many errors do you expect? Well, n times p. What's the variance? It's this much. What's the standard deviation? It's about square root n. Right? So it's something that lends itself to application, just in a wide variety of places. Okay? So now we are going to look at two other random variables, one which we have sort of touched upon implicitly, but not quite explicitly, and then a third one which we haven't touched upon so far. Okay? And the third one is a particularly interesting random variable, which again models a lot of real-world situations. Okay? So, any questions? Now, I'm fairly sure I was belaboring the obvious here. I'm sure most of you know this already. So, I just wanted to get a sense. How many of you got something out of seeing this all over again? Yeah. Okay. And how many of you found it painful to sit through this all over again? Okay, well, sounds like it was a positive thing then. Okay, so let's look at this next distribution, which is called a geometric distribution. Okay. So in the geometric distribution, what we're doing is we again have a coin where the probability of heads is p, but now we are not tossing it a fixed number of times, but instead we keep tossing it until we get the first heads. Okay, so the random variable involved is w, which is the waiting time for the first heads. Okay. Now, if you want to be absolutely rigorous about it, then, if we were to be absolutely rigorous at this point, we'd have to say something about the sample space, because this is not like a sample space we've seen already, in the sense that when we flipped a coin n times, it was clear what the sample space was. Right? The sample space consisted of all possible outcomes when you flip a coin n times, which is what? Well, there are 2 to the n possible outcomes. Each of them is a sample point. Each of them has a probability attached to it. And that's our sample space. Now, what should the sample space be if we toss a coin potentially an unlimited number of times and we're waiting for the first heads? What should the sample space look like? I'm sorry? It is infinitely large, right? Because we can't put an a priori bound on the size of the sample space. Okay? So I just wanted to say this, just to say that if you want to make all this rigorous, you have to say something more. We have to deal with infinitely large sample spaces. But we are going to pretend there's no problem with doing so. Okay, we'll pretend that everything works out, and in fact it does. If you go back and look at how to deal with infinite sample spaces, there's a way to make it all work out. And we won't deal with it here, because it's more complicated than is appropriate for this course. Okay, so I just wanted to mention that so that we are clear, that out here we don't want to look too closely at what the sample space is, because we are afraid of what we'll find. Instead, we are just going to try to analyze this. Okay? Okay, so waiting time for the first set. So what's the probability? W is equal to n. Well, in order that the waiting time is exactly n, it must be the case that you got n minus 1 tails in a row. So this is an event, right? This is an event. And there's exactly one sample point that's consistent with it, which is you got tails, 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 tails. Well, exactly one, I don't know. There are n minus 1 of these, and then you got a heads. Okay, maybe there are many, many sample points. If you keep flipping the coin, now you can have anything you want after that. Right? But if you only flip it n times, this was your heads, well, that's the only possibility that's consistent with it. Right? Now, what's the probability? You must get tails, 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 n minus 1 times, so 1 minus p to the n minus 1. You must get a heads after that, p. Okay. Okay, so again, you can plot this out, and obviously, what is the what should it look like? Well, this would be p, and then the next one would be p times 1 minus p, and then it would keep sort of decreasing exponentially. Right? That's how it would look. Right? Because each time n becomes larger, you get 1 minus p to a slightly larger power. So you're just, if p was half, you are multiplying it by half each time. So you start somewhere half, 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 etc. Right? It's growing down exponentially. Now we could also compute the expected value. Again, that's the probability distribution. We can talk about what's the expected value of x. Well, expected value of x. Now there were different ways of computing this, one way of computing it was the slick way. Right? Remember, there was a very slick way where he said, what's the expected value of W? And he said, well, with probability P, it's 1, right? Because you get heads right away. Okay, so this is probability you get heads. Plus, with probability 1 minus P, you start off with the tails. And now, if you started with tails, how long do you have to wait? Well, here we use the fact that the coin is memoryless, right? It doesn't care that you started with the tails. The expected number of flips before you get a heads after this point, it's as though you started all over again. It's as though you didn't flip this first one. So how long do you have to go? Well, you already flipped one, and now you have to keep going as though you didn't flip it, right? So the amount of time, the number of steps it takes is still the expected value of W. And so now if you if you transpose this to this side, you get 1 minus P times expected value of W subtracted from expected value of W. So you get P times expected value of W equal to P plus 1 minus P. That's 1. So expected value of W equal to 1 over P. Okay. Now, there was a question along these lines in your homework having to do with James Bond. Right? Remember, he was trapped in some place where there were 3 ways out: the air conditioning duct, the sewer pipe, and then there was a door. And each of these required a certain amount of time. The air conditioning duct took a lot of time. It took 1 hour to get through, but then it led to a trapdoor back into the room. The sewer pipe took 2 hours, but it led through a trapdoor back into the room, and the door was just open, so he could walk out any time. So we also assumed each time he was back in the room, if he fell through the trapdoor, he hit his head and suffered from amnesia and chose again uniformly at random from all the 3 choices. So we wanted to know what's the expected time before he got out. So the expected time it takes him to get out. Well, with probability 1/3, he chose the AC, and then it took him 1 hour to get back to the state he was in. It took him 1 hour, and then he was back in the room. So once he was back in the room, he hit his head. So now he's like a coin, back to 1/3 probability. So plus expected value of t. With 1/3 probability, it took him 2 hours through the sewer. And then again, he was back to the same situation, so it still took him expected value of t after that to get out. And with 1/3 probability, he tried the door, and then it took him no time at all to get out. Okay, so now again you can do exactly the same thing we did up there and rearrange, and you get 1/3, 1/3. So you get E of t times 1 minus 2/3. So it's 1/3 E of t equal to 1/3 plus 2/3 equal to 1. So the expected time is 3 hours. Right? Okay. Okay, any questions? Shouldn't we take a 1-minute break? Okay, so we glanced at the calendar recently and realized that the end of the semester is not too far away. And one thing we were thinking about is, well, maybe it's not too early to start thinking about how to make up the final and what, in view of how everybody did in the midterm 2, and so on. And one of the things we were thinking is that it might be helpful, and I wanted to run this by you and see if it's really true. It might be helpful if you were to label the questions as being easy or medium or hard, so that so that people had a sense of what they were attempting. And maybe with a sense that, if you're not, depending upon your ambition level, you can be working on the hard questions or the medium questions, or just, you just do well on the easy questions. And if you're not too ambitious about how well you want to do in the class, you at least do that well. And then if you have time left, you move on to the rest, right? So is that something that might make a big difference, or is it? Yeah? Okay, I'm sorry? It'll destroy your confidence. So I see. Yes? Oh, I see. Okay, how much time we expect you to spend on each problem? Well, so the thing is, we did that already in the sense that, in the previous midterms we said, well, the number of points is a rough measure of how many minutes you should spend on it. But the thought is that, possibly different students want to spend different amounts of time on the problems, and it wasn't clear that everybody chose well about which were the easier problems, which were the harder problems, and so on. And the other thing that I wanted to try to do, and I'm not sure how easy it is to do this, was to see if we can give you such, problems, saying, well, here are some easy problems to try to practice with, here are some medium problems, and so on, or here's, well, okay, so that's not too hard to do. What might be harder to do is sort of to say, well, if you want to achieve a certain level, what are the concepts, at what level should you be trying to understand the material? And because somehow, my sense is that some people, maybe they are getting confused because they are trying to do too much. And if you just want to get a certain understanding of the material, just doing that well is a good idea. And then, once you do that, you can then say, well, okay, let me try to go further than this. But at least you do a certain amount well. Okay, so So anyway, okay, so that's the thought, that we try to provide you with some material that helps you go down this path, if that's a good idea. Yeah? I'm sorry? Oh, I see. Okay, yeah. You're right. Yeah. I know. I always have this experience on airplane flights where there are the easy, medium, and hard Sudoku puzzles, and I always have trouble with the easy ones and manage to do the hard ones. So, yeah, yeah, yeah. Yeah, that's what I really meant. Yeah, yeah. So it could, actually, easy, medium, hard may be a misnomer. It may be, well, how factual they are versus how conceptual, right? So the easier questions, you don't have to get quite as much into the concepts. But maybe it's hard for some people because it involves keeping all this material around, right? So that may be one way of, yeah.
Suppose I'm going to share an experience I had from the first midterm.
Yeah.
Where you said that the last problem was a difficult one, and I actually found it easier than the one on the matching.
Yeah.
Because
No, you're right.
it's a way of looking at things. If you look at it from the right direction, it's easy, but if you don't, it's really confusing.
Yeah.
And what wound up happening is I wound up spending too much time on the problem I was struggling with, and wound up.
Yeah. Okay. So, well, I guess the other way to look at it is that you should view these labels as something helpful, but not necessarily as a total order, because you might think, well, I usually tend to do well on the hard problems. The easy ones stump me, so you go straight for the hard ones and start there. But okay, so maybe the labeling has to be different, and it has to be. Okay, so I don't know what the solution is. Maybe we should think about it some more before going down this path. So, okay, so I'll think about it more and see what we should do instead. Yeah, okay. Right. Okay, so any other? Okay, so let's talk about one more example with the geometric distribution. This is a famous example. It's sort of a, it's a toy problem, but then it's used a lot. It comes up over and over again. Okay, but as it's stated, it's sort of this simple thing where, I don't know if they do this still with cereal boxes. I don't eat cereal, so I don't know. But it used to be the case once upon a time that they used to have coupons in there or little toys or something, something inside the box. So every time you open one, and they come in different varieties, or maybe there were baseball cards in there or something else, right? Something collectible. And so imagine that you have these boxes that you purchase, and let's say that there are n different kinds of cards. Now, of course, in real life, whenever they provide these cards inside cereal boxes or whatever boxes they are not equally likely. Some of them are extremely rare and some of them are not, and so you're left dangling there, with an almost complete set, but then you're waiting for the last one, and it's extremely rare. But let's say that they're all equally likely. Okay, so there are n kinds of cards. Each time you get one of these boxes, you pull out the card, and it's a completely random one out of these n. And you want to know, how many boxes do you need to purchase before you have a complete set? Okay. So, well, let's look at the special case where there are exactly two kinds of cards. So the first box, you get a certain kind of card. Either you get, let's say there are two kinds of cards, 1 and 2. And you either get card type 1 or card type 2. Doesn't matter which one. Let's say you happen to get card type 2, the first box you purchased. And now, how much longer do you have to wait till you get card type 1? How much longer do you have to wait? One over probability of 1, which is a half, right? Probability of 1 is a half, so you need to wait two more turns, right? Expected number of turns. So in other words, you keep going, and you want to know how many times. Well, from here on, you either get to see a 2 or a 1 randomly in each place. We ask, what's the expected number of tries before you see card of type 1? Okay, so you call that a heads. Probability of heads is a half. Expected time before you get a heads is exactly 1 over a half, which is 2. So the waiting time is 1 plus 1 over a half, which is 3. Right? Is it clear how we got there? Okay. So now how do we do the case n equal to 3? Okay, so now there are 3 types of cards. Let's say you still started with card 2, whichever one you started with, and now you're waiting to see 1 or 3. So maybe after this you got 2, 1. Okay, so now you saw 2 different types, and now you're waiting for type 3, and maybe you got again a 1, 2, 2, 1, 1, 3. Okay, so at this point you're done, right? So how can we figure out what's this expected time? Okay, so this is the first time you have a full set of cards, right? You have 1, 2, and 3, all of them, right? So what's the expected time before you got to this stage? So how would we compute that? Okay, so suppose we let x be the random variable which says how long is it going to take? Right? So what we want to know is what's the expected value of x? Okay? But now how can we rewrite x in some other way that's suitable for us? So we could rewrite x as x1, the time it took us to get the first card, which is up through here. So that was always one step, right? The first cereal box you buy, you already saw the first card, right? Some card, some new card. Then we say, here's x2. It's the number of boxes we had to purchase to get the next card after the first one. Right? And then this is x3, the number of steps it took us to find the third card after we already saw the first 2. Okay, so x1 is always 1. x2 might be anything, right? It can be small, it can be large, but what can we say about the expected value of x2? Three. Oh, why is it 3? I'm sorry? 1 over 1/3. So why is it? Okay, so what are we looking for here? 1 or 3, right? So we'll say we have a success if we got 1 or 3. Okay, what's the probability of a success? It's 2/3. right? Because out of 3 possibilities, 2 of them are good for us. So it's like probability of heads equal to 2/3. Okay, so here we have probability of heads equal to 2/3. So what's the expected waiting time? It's 3/2. Right? Okay, now we've already seen 1 and 2. So now we are really waiting for 3. There's only one possible outcome that'll satisfy us. Right? So out of three possibilities, there's only one that will satisfy us. So probability of the heads now is 1/3. So the expected value of x3 is equal to 3. Right? But x equal to x1 plus x2 plus x3. So what's the expected value of x equal to? This plus this plus this, right? Linearity of expectations. So it's 1 plus 3/2 plus 3, which is 5.5. So now let's just do this calculation in general. So what if we have n? So suppose we have n cards. So we can do, how long do we have to wait till we see all n? Well, we do the same thing. We say, well, the first card, it's always something new. Okay, and then we wait until we see the second card, so that's x1, x2, x3, and so on, right, up to x sub n. X equal to x1 plus x2 plus x sub n. Right? And now, what's the expected value of x1? Well, that's just 1. What's the expected value of x2? So now, there's one card that we've already seen. As long as we see any of the other n minus 1 cards, we are happy. Right? So the probability of heads here is n minus 1 over n. Right? Those are the successful cases, all n minus 1 of them. So the expected time is n over n minus 1. What about here? We've already seen 2 of the cards. So n minus 2 are good for us. So probability of heads now is n minus 2 over n. And so the expected value of x3 equal to n divided by n minus 2. Okay. And so the expected value of x is equal to this plus this plus this plus so on plus n divided by 1. Right? So you just get n times 1 over n plus 1 over n minus 1 plus 1 over n minus 2 plus dot 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 plus 1. Okay, or if you want to view it backwards, it's n times 1 plus 1 over 2 plus 1 over 3 plus dot 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 up to 1 over n. Okay? So this thing is called a harmonic series. Okay? And this is very closely approximated by log n to the base e. So this is approximately n times ln n. And the way you see, one of the ways you see that this should, log n should come into the answer is you could view this almost like an integral of 1 over x. Right? An integral of 1 over x is log x, right? So you'd get log n. Okay, let me just say one other thing about the geometric distribution. I'll just say it very quickly. I'll just sketch out why it's true, but I won't actually go through the entire derivation. But you should be able to work it out if you're really interested. So we said for the geometric distribution, the expected value is 1 over p. The expected waiting time is 1 over p. Now, we could also ask, what's the variance of w? And the answer is, it's 1 minus p over p squared. Okay? So think of p as small. Okay, if the probability of heads is tiny, it's like 1 over n. Then the waiting time for heads is n steps. And then it says the variance is roughly n squared. Right? So the variance is fairly large. It's not like independent coin flips. This is really, it's not like the binomial distribution where the expectation was close to n and the variance was also close to n. Here the expectation would be n and the variance would be close to n squared. Okay, if p was small. Okay, so now how do we actually figure this out? Well, one way you could do it is the variance of w equal to expected value of w squared minus expected value of w whole thing squared. We already know that, so we compute the expected value of w squared. So how do we do that? Well, expected value of w squared is summation n equal to 1 to infinity of n squared times probability w equal to n. What's the probability w equal to n? It's p minus 1 to the 1 minus p to the n minus 1 times p. And now, here's where you have to do something tricky because, this is a horrible looking sum, and how do you ever compute it? How do you ever figure out what this is? Well, remember what we did before when we had to compute the sum without an n squared. We said we could view this as a derivative of 1 minus p to the n, right? Because you get n times 1 minus p to the n minus 1 if you take the derivative with respect to p. So now we'd like to view this as a second derivative. Right? Except it's not quite true, right? There's no second derivative here. So what if instead of expected value of w squared, okay, so here's what we do. Okay, so I'm just sketching this. So, if you don't follow this, but the thing to do here is, don't feel responsible for understanding it, but just, let yourself loose and see if you can follow it anyway. And if you do, you should enjoy it, and if you don't, it's all okay. All right, so the way you think about it is, you say, well, if this was the second derivative, then we'd be in good shape again because we'd be summing a geometric series and we'd be doing exactly what we did before with the derivative. But except if it was a second derivative, it shouldn't be n squared, it should be n times n minus 1 times 1 minus p to the n minus 2. Right? That's what we should have here. Right? And then, of course, we can have a p here, and we can also have times 1 minus p times p. So we can have 1 minus p to the n minus 1. We can have a p here. So all this is fine. We could just pull out p times 1 minus p. That's fine. But instead of n squared, we want n times n minus 1. So how do we do that? Well, really, what we want here is not expected value of w squared, but we want expected value of w times w minus 1. Right? So we want variance of w is somehow, if it had been expected value of w times w minus 1 minus expected value of w squared, we'd have been happy, because then we'd have been able to do this summation. Okay? And the point is, expected value of w times w minus 1 is just expected value of w squared minus w. And again, linearity of expectations. This is expected value of w squared minus expected value of W. Okay, so this is what we want, but it's closely related to what we actually have, right? And so what we do is, instead of writing this formula, what we write is variance of W is expected value of W times W minus 1. That's expected value of W squared minus expected value of W plus expected value of W. Okay, so now we've restored expected value of W squared minus expected value of W whole thing squared. Okay, so we work with this formula. And now we can say, this we know, expected value of W is 1 over P. This we know, expected value of W squared is 1 over P squared. This we can compute because now instead of this summation, which we didn't want, this is that summation. Summation n equal to 1 to infinity of n times n minus 1 times 1 minus p to the n minus 2 times 1 minus p times p. Okay, and this thing is the second derivative of 1 minus p to the n. So now you sum the geometric series and take the second derivative with respect to p, and then you figure out what this is. You get it in closed form. Then you substitute 1 over p squared. You simplify, and you get exactly this. Okay? So it's just a very clever way of computing this summation. There's an infinite series, and you want to sum it, and there's just a very clever way of doing it. Okay, any questions? Yeah. Yeah. Okay, sorry. So maybe let me do one or two more steps, shall I? Okay. Okay, so what we want is expected value of W times W minus 1. Okay? So it's summation n equal to 1 to infinity of probability W equal to n, right? So when W equal to n, you'll get W times W minus 1 is n times n minus 1. And then the probability that W equal to n times the probability W equal to n, right? That's the expected value. So that's summation n equal to 1 to infinity of n into n minus 1 into p minus 1 to the n times p. That's the probability W equal to n. Right? The waiting time equal to n, so for it to be n, you must get p, n minus 1 minus p. Sorry. You're right, yeah. Okay, it's 1 minus p to the n minus 1. You must get n minus 1 tails and then heads. Okay, so okay. Can anyone hear that? Okay, we can either... we should either leave or shut the door. Okay. Maybe let's wait for a minute and Andre will let us know what to do. I have to say, during the '89 earthquake, we were in a seminar, and there was a eminent speaker from the East Coast, and this was in Echeverry Hall, where the earthquake doesn't shake the building; it just feels as though a giant hand is crumpling the building, and so the earthquake started, and the audience sort of, everybody sort of, after a moment of hesitation, left. And our speaker, who wasn't used to earthquakes, was, he did not have this, the defense mechanism to actually leave the building. So we had to eventually go back and pull him out. And so. We can't hear anything anymore, can we? Maybe. I think the only responsible thing to do is for me to say, you should leave, and I can stay here and complete the lecture. Oh, my goodness. Oh, thank you. Really? Okay, well, let's do this. I'm sure there's going to be a fire truck outside within a few minutes, and then we'll have to leave anyway. So, do you want to wait for that? And okay. So let me complete this thought, and then in the meantime, But before I do that, let me encourage you to leave. All right. Okay. So back to this. So the first thing to notice is n equal to 1. At n equal to 1, this is 0. So you may as well start from n equal to 2. The second thing you do is you notice that you can pull out p times 1 minus p, and now you get to the n minus 2, and you get rid of this p. Okay, and now you can see that this is the second derivative of 1 minus p to the n. Right? So this is p times 1 minus p times summation n equal to 2 to infinity of d2 by dt squared of 1 minus p to the n. Right? And so now we go ahead and sum, we move the derivative outside the summation, we sum the series, take the second derivative. So you can sum this geometric series in closed form, take the second derivative, and then multiply by that, and you get this. Okay, so let's see. In the few minutes before the fire truck arrives, let's talk about Poisson distributions, which is by the way, it's a very interesting kind of distribution, having to do with rare events like fire alarms. Okay, so the Poisson distribution is actually a it's sort of, it can be a little bit confusing because it's a discrete random variable, and yet it has to do with continuous spaces. Okay, so what is the Poisson distribution about? So, if you were thinking about rare events like radioactive decay or fire alarms, so these are events that can take place anytime, right? So they happen. You have some interval of time, and you want to know how many times did a Geiger counter go off, right? So how many times did it detect a particle being emitted, radioactive decay being emitted, right? And so in fact, when the radioactive decay actually occurs, that's a continuous variable, right? It could happen at any particular point in time, right? But how many times it happened in this interval, that's a discrete set. Okay, so we are thinking of a Geiger counter, where the radioactive decay is happening every so often, so you hear a click, and then there's a pause, and then you hear another click, and then there's a pause, which might be shorter or longer, and then there's another click. And the clicks happen at real, which the time that the click occurs is a real number. But the number of clicks that occur is an integer, is a positive integer, right? Okay, so now it turns out that the interesting thing in this distribution is so we have an interval within which we want to know the number of clicks. Okay, so that's our random variable. X is equal to number of clicks during this interval of time, right? And this number of clicks can be 0 or 1 or 2 or 3 or 4. And what we know is that the expected value of X is some number, lambda. Lambda could be 1 or 2.5 or, E or just some number. Now the claim is, as soon as you know the average number of clicks, you know the entire probability distribution. Okay, so if you know that your Geiger counter is going to emit, it's going to emit 3 clicks during this unit interval, then you can already say what's the probability that it emits 0 clicks, 1, 2, etc. Right? If you know this average number, from this it follows that you know the entire probability distribution. And in fact, you can say the probability X equal to I is lambda to the I divided by I factorial E to the minus lambda. Okay, and if you plot this out, I versus probability X equal to I, then the curve sort of looks like this. So it goes up for a little while, and then it goes down exponentially. Okay? And in fact, this peak occurs close to lambda. So if you look at so lambda would occur something like this, where the peak of this curve. Remember that again, this is a discrete probability distribution. So you have points like this, and the peak is occurring here, and it'll occur at the floor of lambda. Okay. Okay. So now, for this distribution, for this Poisson distribution, we want to figure out a few different things about it. But actually, before we figure out all these things, let me do an example. So. Okay, so let's say that you're looking at a book, and for this particular printing company, on average, you see 1 misprint per page. Okay. Now, what you want to know is what's the probability that you'll actually see 5 misprints in a page, in a particular page. Okay, so you open your book to a particular page, and you see how many misprints there are, You count them up, and you want to know what's the probability there are exactly 5 of them. So it turns out you can represent this, you can model this by a Poisson distribution. Okay, so what is it that gives us a right to model this as a Poisson distribution? Okay, so what happens with the Poisson distribution, again, is, you have this substrate, and the substrate you think of as large. It's continuous or it's large. And you have these events that can happen. The events are random, and that on average, there's a small number of them. There's a finite number of them. And you want to know, but the other thing is, it's like a Geiger counter. If it goes off in this time interval, that is completely independent of whether or not it goes off in this time interval. Right? So if you look at any 2 time intervals, and you want to know, did the Geiger counter go off here versus here? The answer is, whether it goes off here or not doesn't affect whether or not it happens here again. It's completely memoryless, right? And that's true for even the tiniest intervals, right? Okay, so in the case of misprints on a page, why does this apply? Well, we think of these misprints as happening randomly. There are many, many places on a page where a misprint can happen. And if a misprint happens, we are modeling it by saying, well, it doesn't make another misprint more or less likely, right? So if you model this by a Poisson process, then you know the answer immediately, right? So this is the remarkable thing. Okay, so again, let me try to emphasize this fact, because this is sort of what makes probability theory so powerful. It's like understanding mechanics, right? Understanding how forces work, right? The fact that you have an intuitive understanding of how forces work allows you to actually function in the world around you. It turns out that probability theory is a similar thing. There's a very simple theory behind how things work in the world around you. As far as, and there are these very, very simple models which once you understand, you can answer questions which you might think you have no right to be able to answer. So, for example, there's no reason you wouldn't imagine that if you knew on average there's 1 misprint per page that you'd be able to compute exactly what's the probability that you'd see 5 of them. But in fact, this says there's an answer. And the answer is exactly, lambda equal to 1. Right? 1 misprint per page on average. So that's the average number of misprints. So now the probability x equal to 5 is lambda to the 5 divided by 5 factorial e to the minus lambda, which is 1 over 5 factorial e to the minus 1. Right? So that's 1 over 5 factorial times e. If you calculate that, it turns out to be about 1 over 326. Okay? So you can actually put a fairly exact number saying this is the probability that you get 5 misprints. Right? And now you could say, well, what's the probability that if you have a book which consists of 200 pages, what's the probability that there's some page with at least 5 misprints? Right? Well, if in each page the probability of 5 misprints is 1 over 326 with exactly 5 misprints. Okay. So the chance of not having a misprint in a page is 1 minus 1 over 326. The chance of not having a misprint in each of the, not having 5 misprints in each of the 200 pages is this much. And therefore, the probability of having 5 misprints in at least one of the pages is 1 minus that. Right? Does everyone get this? You see, once you say the chance of chance of 5 misprints is exactly 1 over 326, and you want to know what's the chance you get that in any of the 200 pages. The way you get that is by saying, well, the chance of not getting these 5 misprints is 1 minus 1 over 326. Okay? The chance of not getting 5 misprints in any of the 200 pages is this to the 200, and therefore the chance that you do get 5 misprints is 1 minus that. Right? Okay. Okay, so let's see. Okay, so let's compute. So let's now go ahead and try to understand this formula a little bit better. Okay, so we'll understand it better in two different ways. One is we'll make sense out of it by saying, is it a probability distribution? So for it to be a probability distribution, sum over all I of probability x equal to I should be equal to 1. Right, so it should be the case summation I equal to 0 to infinity of probability x equal to I, which is sum I equal to 0 to infinity of lambda to the I over I factorial e to the minus lambda. This should be equal to 1. Okay, so why is that? Well, this summation is equal to e to the lambda. That's a Taylor series expansion of e to the lambda. So e to the lambda times e to the minus lambda is 1. Okay. We can also use this to compute the expected value of x. So we want to make sure the expected value of x is lambda. Right? So we should be able to do that by saying, well, the expected value of x is summation I equal to 0 to infinity of I times the probability x equal to I, which is summation I equal to 0 to infinity of I times lambda to the I over I factorial times e to the minus lambda. And now you can cancel these and you get I minus 1 factorial. Actually, before that, you notice that when I equal to 0, this is 0, so you may as well start the summation from I equal to 1. And now you could pull out a lambda, and you have summation I equal to 1 to infinity of lambda to the I minus 1 over I minus 1 factorial e to the minus lambda. And now you just rename the indices, right? So you can write it as lambda times summation. Let j go from 0 to infinity. J is I minus 1. So j goes from 0 to infinity. So j is I minus 1. So you get lambda to the j over j factorial e to the minus j minus lambda. And remember, this is what we already showed was equal to 1. Right? So what you're left with is just lambda. So the expected value of x is lambda. And that's what we started with, right? We said if the expected value of x is lambda, x is a Poisson distribution, then this is what the distribution function looks like. Of course, that we were asserting, but now we have to go back and check, is the expected value really lambda? And we did, and it is actually really lambda. We can also compute the variance of x. Okay, and to compute the variance of x, actually, let's use the same trick that we used up here, right? Instead of writing variance of x as expected value of x, it's x squared minus expected value of x whole squared. We can also write it as expected value of x times x minus 1 plus expected value of x minus expected value of x squared. So we know what this is. This is lambda. This is lambda squared. Okay. And now we want to know what this is. Right? So what's expected value of x times x minus 1? This is summation I equal to 0 to infinity of I times I minus 1 times lambda to the I over I factorial e to the minus lambda. And now, because we have I times I minus 1, we only want to start from I equal to 2 to infinity. And so we pull out lambda squared times summation I equal to 2 to infinity lambda to the I minus 2, right? Because we pulled out lambda squared. I times I minus 1 cancels with I times I minus 1 here. And we are left with I minus 2 factorial e to the minus lambda. And now we again substitute I minus 2 equal to j. So now j goes from 0 to infinity. So we get lambda squared times summation j equal to 0 to infinity. Lambda to the j factorial e to the minus j, e to the minus lambda. Remember, that's what we showed was 1 up there. So this summation is equal to 1. So expected value of x times x minus 1 is just lambda squared. Okay, so we get lambda squared minus lambda squared plus lambda. These two cancel. And so variance of x equal to lambda. Okay? So the Poisson random variable is it's a random variable with expected value lambda and variance lambda. Okay? Which sort of might it might lead you to believe that it has something to do with the binomial distribution. That's how the binomial distribution behaves, right? The mean and the variance are very closely related. N times p versus n times p times 1 minus p. Right? And in fact, it's for the same reason. In fact, we didn't have to do these calculations. We could have looked behind the scenes and looked at what the Poisson random variable is. What's going on behind the scenes when we say, there's a Geiger counter and there are these clicks every so often. Okay? So if you look behind the scenes, what we are really saying here is that there's a certain model going on. Okay, so what we think of is, what's going on behind the scenes is that there's a genie sitting down here flipping coins, continuously. Okay? So we think of this interval as being divided into n parts. And the genie is sitting there, very quickly flipping a coin, n times, right? And okay, so there's a coin being flipped n times. What's the probability of heads? Well, see, the expected number of heads is lambda, and it's being flipped n times. So what should the probability be? Lambda over n, right? Okay, that way you get lambda heads in n flips. Okay, so this is what's going on behind the scenes, except since it's a genie, n is tending to infinity. Okay, so that's what's happening behind the scenes here in this Poisson process. So we think of, so that's how we are thinking of this as a discrete process that's happening in continuous time, right? And we have all these independence properties which say, if there's a heads in this interval, it doesn't in any way change the fact that there is or isn't a heads in this interval, right? It's just like coin flipping. So there's this coin being flipped behind the scenes. It's being flipped over and over again, almost continuously, right? But the chance of heads is going down as the number of times it's being flipped goes up. Okay, and so now. The probability x equal to I is just the probability that you get I heads when you flip this coin of bias lambda over n times, right? So it's just n choose I lambda over n to the power of I 1 minus lambda over n to the power of n minus I. Okay. And what we are claiming is this tends to lambda to the I divided by I factorial e to the minus lambda as n tends to infinity. Okay? So that's what it means, right? So we are saying if we were to peer behind the covers, what's happening is there's a genie sitting behind here flipping coins, at every moment in time, except that the faster the genie flips the coins, the smaller the chance of heads, right? And it balances out so that the expected number of heads stays at lambda, but the number of times the coin is flipped tends to infinity. Right? That's the Poisson process. So it's just coin flipping, but now you have a finite number of heads, but it's been flipped a very, very large number of times. Okay, so we can do this calculation and see that it does work out. In fact, well, what is this? This is n factorial divided by n minus I factorial lambda to the I divided by n to the I 1 minus lambda over n to the power of n minus I. Okay, so now what do we want? We want the lambda to the I to match that. We want the n to the I, and we want an e to the minus lambda. And the way we get, okay, so let's pull this out. This is lambda to the I divided by I factorial. And now we get n factorial divided by n minus I factorial, n to the I. And then we get 1 minus lambda over n to the power of n times 1 minus lambda over n to the power of minus I. This tends to e to the minus lambda. So between this and this, we got our expression here. Right? Now what we want to do is to show that as n tends to infinity, this piece and this piece tends to 1. Right? And you can see that it tends to 1 because as n tends to infinity, 1 minus lambda over n tends to 0. So this is 1 to the power of minus I, which is 1. Okay, so this... Yeah. This piece tends to 1. And then what about this one? Well, n factorial, n minus I factorial, so you get, the n minus I factorial cancels, so you get n times n minus 1 times n minus 2 ... n minus I plus 1. And then you get n times n times n times n in the denominator, because that's n to the power of I. And of course, when you divide n minus something small by n, you just get 1. Right? When n tends to infinity, this is small by comparison, so this whole thing, this piece also tends to 1 as n tends to infinity. Okay, so this piece tends to 1, this piece tends to 1, you get lambda to the I divided by I factorial, and then e to the minus lambda as n tends to infinity. Okay, so that's all. That's the way that this binomial distribution simplifies into this Poisson distribution. And so it's just much easier to work with, when you have this genie behind the scenes. Okay.